After studying this model, you shall be able to recollect about reducible and irreducible representations, learn how to find tau 3n using Cartesian coordinates as the basis, get tau r and tau t, that is reducible representation based on translational and rotational motion of the molecule. Find tau vibrations after subtracting tau t and tau r from tau 3n. How to find tau vibration for C2V, C3V, TD and DH 4-point group. Now, in this module, we will continue with the vibrational spectroscopy and symmetry aspects of it. We will recollect reducible representations and irreducible representation, as these will be needed for normal mode of analysis and classification of vibrational modes according to symmetry species. Now, let us recollect reducible and irreducible representations. And for this, we will take more examples and find out the irreducible representations. And from there, we will find normal modes of vibrations. And for doing this, let us take the first example of molecule belonging to D4H point group, that is xenon tetrafluoride or PtCl4 2 negative. These molecules both belong to D4H point group, and the molecule xenon tetrafluoride is shown in the figure 1 together with the 3 Cartesian coordinates on each and every atom, that is xenon and 4 fluorine atoms. I am having 15 Cartesian coordinates as the basis. And now we have to make use of the character table of D4H point group, which is also given over here in partial, that is the basis functions have been removed. And we will make use of this and try to find out the effect of various symmetry operations of this molecule in this point group. Now, before going further, let me take the model of xenon tetrafluoride and then what we mean by this, and let us know various symmetry elements in this. This is the xenon tetrafluoride molecules. The white balls, they give me fluorine, and this ball is xenon. This is a square planar molecule as shown over here, and this is my C4 axis in this molecule. And I will be taking all these 5 atoms, 1, 2, 3, 4 and 5 atoms. I will follow the procedure we have already studied, that is when a particular operation of this point group, symmetry operation of this point group, which point group? D4H point group is taken and that is performed on this molecule. Say if I am performing C4 rotation, C4 rotation means 90-degree rotation on these molecules. What happens? All fluorines are shifted. All fluorine atoms are shifted, only xenon atom is not shifted. So, by performing various symmetry operation on this molecule, I will see how many atoms are shifted and how many atoms are not shifted. After making this table, that is how many atoms are shifted, how many atoms are not shifted, I will go for the multiplication factor and then find out tau reducible representation. All these multiplication factors and using Cartesian coordinates as the basis, we have already discussed in detail how to find out tau 3n. Now, the table which is given below that summarizes the effect of various symmetry operations of D4H point group on these 5 atoms, xenon and 4 fluorine. The under number of unshifted atoms in the row, we are finding the figure given is 5. 5 means all the 5 atoms under operation E are not shifted at all. Now, when I take C4 operation, only one atom, that is a xenon atom, is not shifted. Similarly, you can go for C2, which lies along C4 axis. That also gives xenon atom is not shifted. If I take C2, that is along the diagonal, and C2 bisecting the diagonal, I am having C2 dash and C2 double dash. C2 dash is along the diagonal, so 3 atoms are not shifted. C2 double dash bisecting the opposite bonds, only one atom, that is xenon, is not shifted. I, only xenon is not shifted because center of inversion lies at the xenon. Fluorine, they are interchanged. Like this, we are having the effect of S4, sigma H. How many? It is the same as the effect of E. All the 5 atoms, they remain. Then sigma V, that is all the 3 bond, 2 fluorine, 1 xenon is not shifted, and then sigma D only. So, I am having now the figure 5 1 1 3 1 1 1 5 3 1, and after multiplication factor corresponding to symmetry operations, we have tau reducible as 15 1 minus 1 minus 3 minus 1 minus 3 minus 1 5 3 and 1. Now, this tau 3 1 can be reduced to irreducible representation by following standard reduction formula. That is, in this D4H point group, what are the various irreducible representations that are present into this, and after reduction the result comes out to be A1G, A2G, B1G, B2G, EG, 2A2U, B2U, 3EU. That is, we are having total this, and the sum for this is again whatever 1 plus 1, if you write down the dimension, total dimension is 15. Now, let us take this is the way we are getting. We can take the example of CCl4, CH4, ruthenium tetroxide, SO4 2 negative. All these molecules, they belong to TD point group. Total symmetry, number of symmetry operation in TD point group are 24. Therefore, order of the group is 24. Sum of the symmetry elements and 3n vectors for CCl4 molecules are shown into the figure. With the help of the module, let us show the CCl4 molecule like this. It is a tetrahedral molecule. If I take this is my C3 axis. Like this molecule has 4 C3 axes, one along like this, another like this, and like this. So, this molecule has 4 C3 axes, and this is plane passing through this by taking this and this and passing through like this. That is, it is like this. Similarly, the plane like this, and similarly the plane like this. Also this molecule has C2 axis. If I take the molecule like this, and this is my rotation axis, I can rotate through 180 degree. I can rotate through 180 degree. So, I am having this CCl4 molecule. It has 5 atoms, 1, 2, 3, 4 and 5. On each atom, I put down 3 Cartesian coordinates, x-axis, y-axis, z-axis. So, 3 on this, 3 on this, 3 on this, 3 on this and 3 on this. Total 15 Cartesian coordinate vectors. And now I will see how atoms are shifted. If I perform C3 operation on this molecule like this, how many atoms are shifted? Only the plane, these and these, they are shifted. This and this do not shift. So if I carry out C3 operation, only 2 atoms are not shifted. Now if I carry out C2 operation like this, I perform like this. How many atoms are not shifted? Only 1 atom is not shifted. These and these, they are interchanged. So like this, I can study the effect of symmetry operation on this molecule. Now let us see the effect of various symmetry operation of CCl4 molecule on these 15 Cartesian coordinates. And these effects are summarized into this. That is, the number of atoms unshifted are given as 5, 2, 1, 1 and 3. That is, 5 atoms are unshifted when symmetry operation E is carried out, and when C3 operation is carried out, 2 atoms are unshifted. When sigma V or sigma D is carried out, 1 atom is unshifted. Like this, we can carry it out. That is, when sigma D is there, it contains 2 chlorine atom and 1 carbon atom. So unshifted atom is 3. So we are having the figure as 5, 2, 1, 1 and 3. We go for multiplication factor and we get the tau reducible as 15, 0, -1 and 3. And this tau 3n can be reduced by following the standard reduction formula, and the result is tau 3n is A1 plus E plus T1 plus 3, 2. Total irreducible representations are, which is 1 plus 2 into 1 plus 3 into 1 plus 3 into 3, that is 15, which is equal to the sum of characters of E in irreducible representation tau 3n. I have taken 2 examples with you, that is xenon tetrafluoride and your CCl4 molecule. The results from other molecules, that is C2V point group, molecules are SO2 and water molecules. The result is 3A1 plus A2, 2B1 plus 3B2. For POCl3, ammonia, CHCl3, that is C3B point group, the result is tau 3n is equal to 4A1 plus A2 plus 5A. For xenon tetrafluoride, we have already seen what is the result: A1G, A2G, B1G, B2G, EG plus 2A2U plus B2U plus 3U. And for tetrahedral CCl4, etc., we are having the result as A1 plus E plus T1, 3, T2. All these examples have been discussed in earlier modules. Here again I have repeated only 2. Now let us go for the further into this. How to find out only tau vibration into these molecules? Now in order to get tau vibration into these molecules, now we have to look for the 3n vectors as the basis. The 3n base vectors include total translational plus rotational degrees of vibration. But we are interested in irreducible representations that are given only by vibrational stretching or deformation vectors. The result for tau 3n include the result for rotational and translational vectors also. Tau 3n therefore is equal to tau vibration plus tau r plus tau t, where tau vibration represents results due to stretching and deformation angle only. Tau r represents results for rotational vectors and tau t represents results for translational vectors. In order to get pure tau vibration, we have to subtract the sum of tau r plus tau t from tau 3n. Therefore, tau vibration is equal to tau 3n minus sum of tau r plus tau t, or tau 3n vibration is equal to tau 3n minus tau r minus tau t. How to find out the sum of tau r plus tau t? For this, we will consider our 4 examples, that is C2V, C3V, D4H and our tetrahedron. In modules on representation, we have learned how to use x, y, z vectors along Cartesian coordinates, which form the basis for reducible representation. We have also seen the result for Rx, Ry, Rz rotational vectors. All these information that for which irreducible representation x, y, z, Rx, Ry, Rz vectors form the basis is given in the character table of the point group of the molecule. So, we have not to bother for finding these irreducible representation every time by performing symmetry operation. What you do, you just look the character table and go to the basis function against the particular irreducible representation. Let us take the water molecule in little bit detail. The tau 3n for water molecule is 3a1 plus a2 plus 2b1 plus 3b2. In table of C2V point group, against irreducible representation, that is, I take the irreducible representation a1, a2, b1, b2, and in column 1 are listed basis set, that is, which basis set form the basis for which reducible representation. Or I can say, I have to now look x, y, z, Rx, Ry, z, the basis functions, and see which are the basis for which irreducible representation. First, let us take Rx, Ry, Rz rotational vector as the basis and find irreducible representation. Let us take Rx rotational vector. First, see for which irreducible representation it is the basis. In the character table, if we look for B2, what you find? You go from B2 to the column 1, you find here it is Rx or Ty. So, Rx represents B2 irreducible representation. Let us take Ry rotational vector. First, see for which irreducible representation it is the basis. In character table again for C2V point group, we find against B1 there is Ry and Tx. So, Ry represents B1 irreducible representation. Let us take Rz rotational vector. First, we see for which irreducible representation it is the basis. In character table, it represents A2. It represents A2, that is Rz. So, thus Tr is, that is from this, Tr is B2 plus B1 plus A2, that is total Tr is Ry, Rx, Rz, and against them we are having irreducible representation as B2 plus B1 plus A2. Similarly, let us take translational vectors Rx or x, Ty or y, Tz or z as the basis and find irreducible representation for which these are the basis. Let us take Tx or x translational vector and find the corresponding irreducible representation. What you get? You see the table, x, Tx or y is against B1. So, it is Tx or By represents your B1. Let us now take Ty or y translational vector and find corresponding irreducible representation. Here what you find? Against B2 I am having Ty, that is Ty is the basis for B2. Thus Ty or y represents B2. Let us take Tz or z translational vector and find corresponding irreducible representation. Again this partial table, A1 is your Tz or z. Thus Tx or x, Tyy or Tzy vectors correspond to B1 plus B2 plus A1. So now we are having tau t is equal to B1 plus B2 plus A2. From equation 1 and 2, that is equation for tau r and here tau t, we are having the results from 1 and 2 as tau r plus tau t is equal to B2 plus B1 plus A1, B2 plus B1 plus A1, that is tau r plus tau t is 2B1 plus 2B2 plus A1 plus A2. Tau vibration is equal to 3n minus tau r plus tau t, that is tau 3n minus tau r minus tau t. But tau 3n is 3A1 plus A2 plus 2B1 plus 3B2, or tau vibration is equal to 3n minus tau Tr plus T, or tau 3n minus tau r minus T, or I am subtracting 3A1 plus A2 plus 2B1 plus 3B2 minus 2B1 minus 2B2 minus A1 minus A2, and the result is tau vibration is 2A1 plus B2. There are 3 atoms in water molecules, so there should be 3n minus 6 vibrational modes. These should be 3 vibrational modes. The irreducible representation 2A1 plus B2 equals to 3 modes of vibration. These are one dimensional, so these are the 3. Now, let us take another example of C3V point group and follow the procedure which I have described for finding tau vibration for water molecule. And I take the example of POCl3. In POCl3, again it is a molecule which has see-through V symmetry, and if we just look up the back of this part lecture, you find tau 3n is 4A1 plus A2 plus 5A. In table for CV4 point group, against irreducible representation A1, A2 and E, I look the column again, last column, and try to find out which is the basis function for this. That is, I have to look x, y, z or Rx, Ry or Rz. Let us take the character table of C3V point group and concentrate on x, y, z, Rx, Ry, z. That is the last column we see basis function, and try to find out this basis function correspond to which irreducible representation. And for that, let us first take Rx, Ry, Rz rotational vector as the basis and find out for which irreducible representation these are responsible. Let us take Rx and Ry rotational vector and see for which irreducible representation these are the bases. Let us see the partial character table. You find the irreducible E, which has the character plus 2, minus 1 and 0. And in the last column we are having x and y grouped together, Rx and Ry grouped together. Rx and Ry form the basis for E. Similarly, x and y or Tx and Ty form the basis for E representation. Rz vector is the basis for A2. You look the character table in partial, look the A2 irreducible representation for which I am having plus 1, minus 1 as the character. So, against that there is a Rg. Z or Tz vector is the basis for A1. Again look the character table and partial part is A1. Before that I am having Rz. So, tau r plus tau t equals to tau r plus t is equal to A1 plus A2 plus 2E. But tau 3n is 4A1 plus A2 plus 5E. Therefore, tau vibration is equal to tau 3n minus sum of tau r plus tau t is equal to 4A1 plus A2 plus 5E minus A1 minus A2 minus 2E, that is 3A1 plus 3E. There are 5 atoms in POCl3 molecule. So, there should be 3n minus 6 vibrational modes. There should be 9 vibrational modes. The irreducible representation 3A1 plus 3E equals to 9 modes. 3 plus 3 into 2. As there are 3 one-dimensional irreducible representation and 3 two-dimensional irreducible representations. Now, let us take another example of CCl4 molecule, carbon tetrachloride, which belongs to TD point group, and work out the total number of vibrational modes for this molecule. Now, in this module, earlier we have learnt, I have revised, or we have learnt again the CCl4 molecules and found tau 3n, and the result obtained were A1 plus E plus T1 plus 3T2. Let us look the table for TD point group and try to look for x, y, z, Rx, Ry, Rz vectors in the last column, and also see the irreducible representation A1, A2, E, T1, T2, and try to match the two columns, that is the which match with the which. Now, here what I find over here, if I take Rx, Ry, Rz in the last column where it is written linear function rotation, what I find Rx, Ry, Rz, they are against T1, that is T1 irreducible representation. The basis function is Rx, Ry, Z. Now, if I take x, y, z, they form the basis for T2 as they are listed against T2 irreducible representation. Now, what we find over here, that is T1 irreducible representation Rx, Ry, Rz are the basis. For T2, x, y, z are the basis functions as shown over here in the partial table. So, what we find, our net result is tau r plus tau t equals to tau t plus tau r T1 plus T2, or tau 3n is A1 plus E plus T1 plus 3T. To get tau vibration, we take tau 3n, subtract the sum of tau r plus tau t, and the result is A1 plus E plus T1 plus 3T2 minus T1 minus T2, and the result is A1 plus E plus 2T2. There are 5 atoms in CCl4 molecules. So, there should be 3n minus 6 vibrational mode. There should be 9 vibrational modes. The irreducible representation A1 plus E plus 2T2 equals 9 modes, 1 plus 2 plus 2 into 3 times. And these, there is one one-dimensional irreducible representation, one two-dimensional irreducible representation, and two three-dimensional irreducible representation. So, in this module 30, we have refreshed our memory about reducible and irreducible representations. How to find tau 3n has been explained again for C4V and D4H point group, that is CCl4 and xenon tetrafluorine. Number of other examples have been worked out for C2V, C3V, D4H and TD point group, and just by looking the character tables, how to find tau t, tau r has been explained, and once tau t and plus tau r are known, tau 3n, using tau 3n, tau vibrations can be obtained by subtracting from tau 3n the sum of tau t plus tau r, that is, we are getting tau vibration. Now, in this module only we have learnt up to this place, that is just by making use of the molecule, its point group, and by knowing the number of atoms into the molecule, we can find out the total number of expected tau vibrational, that is, total number of vibrational modes into the molecule. In further modules, we will learn about the activities of these vibrational modes.